Okay, we're continuing with section 6.1, extending the particle in uniform circular motion. This is the second part, and we're going to talk about some analysis models. Where's, I've forgotten my, here we go. All right. Imagine a moving object that can be modeled as a particle. If it moves in a circular path of radius r at a constant speed v, it experiences a centripetal acceleration. Because the particle is accelerating, there must be a net force acting on the particle. That force is directed toward the center of the circular path and is given by the sum of the forces equals mass times acceleration. Well, we know the centripetal acceleration is v squared over r, so it's equal to mass times v squared over r. Some examples, sorry about that. Some examples are the tension, examples that cause the forces, centripetal force. The tension in a string of constant length acting on a rock twirled in a circle. The gravitational force acting on a planet traveling around the sun in a perfectly circular orbit. The magnetic force acting on a charged particle moving in a uniform magnetic field. And the electric force acting on an electron in orbit around a nucleus in the Bohr model of the hydrogen atom. Now, let's go to that first one. The tension in a string of constant length acting on a rock twirled in a circle. If you've ever played tetherball, you know, where the ball is tied to a rope and the rope wraps around the string, you'll notice that as the string gets shorter, as it wraps, the ball starts going faster. So that's not constant velocity. So we can't use that as an example. The string has to be of constant length. Okay. A small ball of mass m is suspended from a string of length L. The ball revolves with a constant speed v in a horizontal circle of radius r as shown in the figure. Because the string sweeps out the surface of a cone, the system is known as a conical pendulum. Find an expression for v in terms of the length of the string and the angle it makes with the vertical in the figure. Now let's imagine the motion of the ball in the figure and convince yourself that the string sweeps out a cone and that the ball moves in a horizontal circle. Now the ball in the figure does not accelerate vertically. Therefore, we model it as a particle in equilibrium in the vertical direction. So in this direction, it's in equilibrium. The sum of the forces equal to 0 in that case. It experiences a centripetal acceleration in the horizontal direction. So it is modeled as a particle in uniform circular motion in this direction. So it's in equilibrium vertically, but it is a particle in uniform circular motion horizontally. That's how we look at it. Okay, let theta represent the angle between the string and the vertical. In the diagram of forces acting on the ball, the force T exerted by the string on the ball is resolved into vertical component T equals cosine theta, and a horizontal component T equals T sine theta. I hope I said that correctly. Vertical component T cosine theta and horizontal component T sine theta, acting toward the center of the circular path. So let's apply the particle in the equilibrium model in the vertical direction. So the sum of the forces, that's T cosine theta and minus mg, they equal to 0. So T cosine theta equals to mg. They have to be equal to balance out. Okay, let's go on. Use the equation from the particle in circular motion model in the horizontal direction. That's this one. The sum of the forces in the x direction equals T sine theta, and that's equal to the mass times the centripetal acceleration, which is equal to the mass times v squared r, because the centripetal acceleration is v squared r. Okay, divide the two equations and use the sine theta over cosine theta equals tangent. Excuse me. So if we divide these two, we have the t cancels, so we have sine theta over cosine theta is tangent, and we have, let me move this, we have mv squared r, mv squared divided by r divided by mg. So we end up with the m's cancel, and we just end up with v squared over rg. Okay. Now let's solve for v. There we go. So v is equal to rg tangent theta. You just multiply both sides by rg, you get rg tan theta equals to v squared. Well, we have to take the square root of both sides to get v, and we get the square root of rg tangent theta. Okay, let's incorporate r equals L sine theta from the geometry in the figure, the L being the length of the string, and the radius is equal to L sine theta. So V equals the LG sine theta times tangent, LG sine theta times tangent theta. So the R, the radial distance, is L sine theta. Okay, let's notice that the speed is independent of the mass of the ball. Consider what happens when theta goes to 90 degrees so that the string is horizontal. Because the tangent of 90 degrees is infinite, the speed v is infinite, which tells us that the string cannot possibly be horizontal. If it were, there would be no vertical component of the force T to balance the gravitational force on the ball. Okay. Now, another example. A puck of mass 0.5 kilograms is attached to the end of a cord 1.5 meters long. The puck moves in a horizontal circle as shown in the figure. If the cord can withstand a maximum tension of 50 newtons, what is the maximum speed at which the puck can move before the cord breaks? Assume the string remains horizontal during the motion. Okay, let's conceptualize this. It makes sense that the stronger the cord, the faster the puck can move before the cord breaks. Also, we expect a more massive puck to break the cord at a lower speed. Imagine whirling a bowling ball on the cord. We can categorize this as follows. Because the puck moves in a circular path, we model it as a particle in uniform circular motion. Okay, let's incorporate the tension and the centripetal acceleration into Newton's second law. The tension is equal to mass times the centripetal acceleration being v squared over r. So the tension is equal to m times v squared over r. Now let's solve for v. So we multiply both sides by r and divide by m. We'll get v squared equals tr over m. And so that gives us v equals to the square root of tr over m. Now let's find the maximum speed the puck can have, which corresponds to the maximum tension in the string that the string can withstand. V max is equal to T max, the max tension times the radius divided by the mass. You put in the numbers, and you get 12.2 meters per second. The equation for V shows that V increases with T and decreases with larger M, as we expected from our conceptualization of the problem. So if you increase T, V increases, and if you increase M, V decreases. Okay. Now suppose the puck moves in a circle of larger radius at the same speed. At the same speed v, is the cord more likely or less likely to break? Well, let's look at the centripetal acceleration. The centripetal acceleration formula. The centripetal acceleration is equal to v squared over r. Now, if something that is in the denominator, if it gets bigger, the thing on the other side of the equal sign gets smaller. So if the radius gets larger, the acceleration goes down. That basically what that means is that the acceleration inward is less, and the velocity vector is not changing as much. The larger radius means that the change in the direction of the velocity vector will be smaller in a given time interval. Therefore, the acceleration is smaller and the required tension in the string is smaller. As a result, the string is less likely to break when the puck travels in a circle of larger radius. So it's less likely. Okay. Now, let's look at this problem. What is the maximum speed of the car? A 1,500 kilogram car moving on a flat horizontal road negotiates a curve as shown on the overhead view in the figure. If the radius of the curve is 35 meters and the coefficient of static friction between the tires and the dry pavement is 0.523, find the maximum speed the car can have and still make the turn successfully. Okay, let's conceptualize this. We can imagine that the curved roadway is part of a large circle so that the car is moving in a circular path. We categorize this as follows. Based on the conceptualized step above, we model the car as a particle in uniform circular motion in the horizontal direction. The car is not accelerating vertically, so it is modeled as a particle in equilibrium in the vertical direction. Okay. Let's analyze this. The back view of the figure shows the forces on the car. The force that enables the car to maintain its circular path is the force of static friction. It is static because no slipping occurs at the point of contact between the road and the tires. If this force of static friction were zero, for example, if the car were on an icy road, the car would continue in a straight line and slide off the curved road. The maximum speed Vmax the car can have around the curve is the speed at which it is on the verge of skidding outward. At this point, the friction force has a maximum value. The static friction max is equal to mu sub s times n. Mu sub s being the coefficient of static friction and n being the normal. Let's apply the equation from the particle in uniform circular motion model in the radial direction for the maximum speed condition. So Fs max is equal to mu sub s times n, equals to mass times acceleration, centrifugal acceleration. So those two have to be equal. The friction force and the mass times acceleration have to be equal. Apply the particle in equilibrium model to the car in the vertical direction. The forces in the y direction have to equal zero because the car isn't moving up and down either way. So the normal is equal to mg. So let's solve the first equation for the maximum speed and substitute for n. If we solve for v, since we get the square root of mu sub s, the coefficient of static friction times the normal times the radius divided by the mass. Well, the normal is mg, so we end up mu sub s mg over times r divided by m. Well, the m's cancel, and so the v max is equal to mu sub s times gravitational acceleration times the radius, square root of mu s g r. Now let's substitute the numerical values. Vmax is equal to 0.523, that's mu sub s, 9.8 meters per second squared, of course, is the gravitational acceleration, and 35 meters is the radius. And we end up with 13.4 meters per second. Now, this speed is equivalent to about 30 miles per hour. Therefore, if the speed limit on this roadway is higher than 30 miles an hour, this roadway could benefit greatly with some banking, as in the next example. Notice that the maximum speed does not depend on the mass of the car, which is why curved highways do not need multiple speed limits to cover the various masses of vehicles using the road. Now, suppose a car travels this curve on a wet day and begins to skid on the curve when its speed reaches only 8 meters per second. What can we say about the coefficient of static friction in this case? Okay, let's, the coefficient of static friction between the tires and a wet road should be smaller than that between the tires and a dry road. This expectation is consistent with experience with driving because a skid is more likely on a wet road than a dry road. That's happened to me, and it wasn't fun. I ended up in a small accident. To check our suspicion, we can solve our equation for the coefficient of static friction. And Vmax is equal to mu sub s times gr. Mu sub s equals Vmax squared divided by gr. Now, substituting the numerical values gives mu sub s is equal to 8 meters per second squared divided by g, 9.8 meters per second squared, divided by the radius, 35 meters, and you get a coefficient of static friction of 0.187, quite a bit less when the road is dry. The regular coefficient was 0.523 for the dry road. Let's take another break here before we continue with more examples on section 6.1.